Welcome to video 6.3. In video 6.2 we talked about electron configurations and orbital diagrams. So we're going to talk, and we talked briefly about noble gas notation, and it's where we use the noble gas symbols and brackets to shorten inner electron configurations of other elements. So remember that the noble gases are found in group 18. So if you look on your periodic table, helium, neon, argon, krypton, xenon, radon. Those are our noble gases. So what I can do is I can use those to shorten my electron configuration so I don't have to keep writing it over and over again. So remember yesterday we wrote strontium's electron configuration, and we're going to write it again. And strontium has 38 electrons. So when I write strontium's electron configuration, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. And that adds up to an equal 38 electrons. Well, if I wanted to write the noble gas shortcut for this, what I would do is I would find strontium on the periodic table. And strontium is on the 5th period, so it's on the 5th row of the periodic table if you count down. Hydrogen starts the 1st period, lithium starts the 2nd period, sodium starts the 3rd period, potassium starts the 4th period, and rubidium starts the 5th period, and strontium is next to rubidium. So what I'm going to do is I'm going to look at strontium, and I'm going to drag my finger over, and the noble gas on the 5th period is xenon. But xenon has 54 electrons, and strontium only has 38. So I can't use xenon to write the noble gas shortcut. So I have to go to the noble gas above xenon, which is krypton. And krypton takes care of 36 electrons. So when I am writing the noble gas shortcut, I'm going to use the noble gas that ends the period or the line above it. So if krypton takes care of 36 electrons, I do 38 minus 36 because 38 is strontium's number of electrons and 36 is krypton's electrons. And I've got 2 electrons that still need a home. So then I'm going to start, since strontium's on the 5th period on the periodic table, I'm going to start at 5s. I can't start at 1s because strontium is not on the 1st period. It's on the 5th period. So I'm going to start at 5s, and the s orbital can hold 2 electrons. So that is it. That's all I have to write for my noble gas shortcut for strontium. What that basically tells me is I just cut out all of this right here because krypton, with its 36 electrons, writing that noble gas in brackets takes care of writing all that I wrote in brackets for the electron configuration. So, what we're going to do is we're going to look at these, these elements that yesterday in the previous video, 6.2, we wrote as electron configurations. Now we're going to write them as noble gas notation. So I look at carbon, and carbon has 6 electrons. And so it's on the 2nd period. I can't use neon, which is what ends the 2nd period, because neon has 10 electrons. So I'm going to use helium. It's the noble gas that ends the period above it. And then I'm going to start with 2s because carbon is on the 2nd period. So all of its electrons, what I'm going to do is I'm going to take that carbon has 6 electrons. Helium takes care of 2 of those. So I've got 4 electrons left. I can't put all 4 of those with the s orbital. I can only put 2 with the s orbital. But then I can go to the p orbital. I just follow the alphabet from 2s. The p orbitals can hold up to 6, so I can put 2 right there. If you go look at your notes from yesterday, carbon's electron configuration, the ending looks a lot like the noble gas notation. So now let's look at zirconium. And zirconium has 40 electrons, so I'm going to go ahead and write that down here. And zirconium is on the 5th period on the periodic table, so go find it. And the element that ends the 5th period is xenon, but zirconium has 40 electrons and xenon has 54, so that won't work. So I look at the noble gas above xenon, which is krypton, and krypton has 36 electrons. So I'm going to do 40 minus 36, and I've got 4 electrons that need a home. Well, the thing that I have to remember is that zirconium is on the 5th period. So I'm going to start with 5s. So remember, the s orbital holds 2 electrons, so the 5s2, and then I follow the alpha val. After 5s2, I'm going to go to 4d, and it could hold up to 2, but up to 10, but I've only got 2 left, so that's going to be 4d2. Alright, now let's look at lead. And lead has 82 electrons, and it is on the 6th period. So I am going to not choose radon, because radon has 86, even though it ends the 6th period. I'm going to choose xenon. So I'm going to put xenon in brackets, and that takes care of 54. So 82 minus 54 is going to be 28, I believe. So I've got 28 electrons that need a home. So xenon ends the 5th period. Lead is on the 6th period. So I'm going to start 6s2. So now I've got 26 electrons that need a home. And after 6s, I go 4f. So 4f, 14. And then I go 5d, 10. And then I go, so that took care, that got me down to 12. Now I'm not down to 2. And so I'm going to go 6p2. And then uranium. Remember, uranium had 92. And uranium, remember in the periodic table, you take the lanthanides and you take the actinides and you shove them up into that gap. So uranium is technically on the 7th period. So I am going to not use unoctium. I'm going to use radon. And radon has 86 electrons. So now I've got 6 electrons that need a home. And since uranium is technically on the 7th period, I'm going to start 7s2. And then I'm going to go 5f14. So that is how I write the noble gas notation. So make sure you practice that. It's a lot shorter than writing the full electron configuration. So remember that electron configurations, they're going to be telling me, they give me where the element is the most stable, where the electrons are going to be when the element is the most stable. And just as a review, the s sublevel has 1 orbital, you've got 2 electrons in it. The p sublevel has 3 orbitals, it's got 6 electrons in it. The d sublevel has 5 orbitals, it's got 10 electrons in it. And the f sublevel has 7 orbitals with 14 electrons. If you look at the periodic table, one thing you will notice is that it's shaped really funny. The reason for this is because the first 2 columns are the s block. And remember, the s orbital can hold 2 electrons in it. So everything in the first column is actually going to have an ending of its electron configuration. It's going to be S1. Everything in the second column is going to end S2. And helium is just a little bit weird, and it acts like a noble gas, but it actually belongs in the S block. The reason that the P block is 6 wide is because it can hold up to 6 electrons. So this would end up P1, that should also be a 1. P2, P3, P4, P5, P6. Go back and check. If you look at carbon, carbon is in the second element in the P block. on that first row, and it ends P2. So, and then the D block, it is conveniently 10 across because it corresponds to what we had before. It corresponds to that number, 10. And then the F block going across is going to be 1, and it's going to be F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, F12, F13, and F14. So that is where the numbers come from. If you look, the ending should correspond with that. If you also look, this is going to be energy level 1, 2, 3, 4, 5, 6, 7. And the D block, it's almost like you scooted it up. It's going to end up being row 3, row 4, row 5, row 6. And then the F block would be rows 4 and 5 is basically how that works. The P block also corresponds to the number, the period on the periodic table that it is. So what this also tells me is it tells me the number of valence electrons. And the valence electrons are the electrons in the atom's outermost energy level. So whatever is that highest number. So I can do the electron dot structure, and that tells me the element symbol, and it represents the nucleus surrounded by dots representing the element's valence electrons. So I can get the electron configuration I can get the electron dot structure from the electron configuration. So it also follows the column that is in. So if it is in column 1, it's going to have 1 valence electron. If it's in column 2, it's going to have 2 valence electrons. If it's in column 13, it's going to have 3 valence electrons. Group 14 is going to have 4 valence electrons. Group 15 is going to have 5 valence electrons. Everything in group 16 is going to have 6 valence electrons. Everything in group 17 will have 7 valence electrons. And everything in group 18 will have 8 valence electrons, except for helium, which has 2. So, we're going to draw the electron dot structure for the following elements. Sn is 10. And when you look up 10, it is in group 14. So that means it's got 4 valence electrons. 1, 2, 3, 4. If you look up magnesium, it is in group 2. So magnesium has 2 valence electrons. 1, 2. If you look up krypton on the periodic table, it's in group 18. So that means it has 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. So let's double check this. Let's look at magnesium. It's got 12 electrons total, but it's only got 2 valence electrons. Well, let's look at its electron configuration, which would be 1s2, 2s2, 2p6, 3s2. Well, 3s2, that's my valence shell. It's the highest energy level, and there's 2 electrons in it. That's why magnesium has 2 valence electrons. So remember that the electrons in the highest energy level are called valence electrons. We've gone through this again, but it can't hurt to remember that group 1 has 1 valence electron. That goes for hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, all the way down that column. So the number of valence electrons always corresponds to the column it's in. So let's think about strontium right here. It has an electron configuration of Kr5s2. Looking at just that, what is the group, period, and block? So remember, the group on the periodic table is the column it's in. The period is the row, and the block is just S, P, D, or F. So when I look at this right here, the 5 tells me the period it is in.